right, welcome. So let's see. Well, we still have 1 minute to start. So we're going to give it another minute or two. So let me see how many participants we have. We have 13 participants. So let's give it another minute or two so that we're going to get enough participants before we start. Meanwhile, can everyone hear me? If you can, press yes on your participants list on Zoom. Okay, so it's working well. I'm very surprised that Zoom is actually holding up this well. It's quite amusing how many online chats are happening and the idea how much bandwidth must be consuming. It still works well. Okay, so 15 participants. Let's wait for 20 participants and then we're going to continue from there. So while we are waiting for more students to show up, I'm sure you already have seen the Campus Wire post about the announcement on two things. One is the final exam, and then I already announced it earlier, but the final exam is going to be given as an online assignment on Gradescope, meaning that you will be able to answer all the questions online. You won't need to write down anything with your hands and take a picture or anything like that. You're going to just answer it on your browser, and then you're going to be given 3 days. 3 days to answer all the questions, and then it's going to be open book. You're free to read whatever the material you need in order to answer all those questions. Only thing is that I do ask you to answer those questions yourself on your own, right? Because the goal of these exams is not to give you, distinguish all those students across different, the whole spectrum of the letter grades, but, like the goal is for you to learn all the materials as well as you can so that you can be prepared to go work in a company where you use the machine learning algorithms, or you go on a grad school studying further machine learning. And then the second item in that announcement was about the homework policy. So although this course has been very strict about the homework policy in a sense that you have to submit something, and then I emphasize it further and further, but in light of the COVID-19 situation, it's pretty clear that not everyone has the same kind of resources, nor time, nor even the mental capacity to finish all the homeworks in time, which is totally understood. This is a pretty crazy situation. And then there are some issues with the moving out of the dorms and so on. So even if you have not been able to submit the homework assignment, that's fine. You're going to just get 0 for that particular homework, but you're not going to fail the course. And then at the end of the day, I'm going to try to curb the scores in order to make sure that the letter grades that you're going to get are not going to be unfairly impacted by the current situation of the pandemic. So please be a bit more relaxed. I know that there are a lot on your plate at the moment, and trying to, focus on your family, your well-being, and then you have the machine learning from there on. Okay, we have 24 participants. And as usual, whenever you have a question, of course, you can email me, but if it's about the content of the course, it's best to ask questions on Campus Wire so that any of the course assistants or I can answer your question, and then thereby letting all the other participants or your peers to see the questions and answers as well. That's going to be win-win, right? Literally. So today, we are going to go back to k-means clustering and then trying to generalize the notion of clustering into the probabilistic modeling. And if you remember from the probabilistic machine learning or the Bayesian machine learning that we talked about earlier, is that in the context of the linear regression, what we meant by probabilistic machine learning or any kind of probabilistic modeling is that we try to treat as many items or the variables in our machine as random variables. And in the case of clustering, what are those random variables that we can think of? Let me see. Our observation has to be a random variable, right? So our observation, let me use the dark one. Our observation X is going to be a random variable now. And then this is going to be the dimensional random variable. And then this is, not unlike what we have seen so far, right? And then what other random variable can we have? We probably can introduce a z as an assignment random variable. So this is a random variable that's going to be the prime dimension. And then it's going to be 1/2. And then this random variable z tells us about the assignment. That is, given some observation x, this z, the random variable, is going to tell us to which cluster this x, the observation, belongs to. Now this is interesting, and then of course it's a 1/2 vector out of the d prime dimensions or k dimensions. If you want to make an analogy to the k-means clustering more clearly, this must follow the categorical distribution, right? And then categorical distribution, we learned it from the multi-class classification or the Softmax classification earlier, which feels like, that was like years ago, but a few weeks ago. Now, when we have these two variables or random variables, what did we learn that we have to do in this kind of probabilistic modeling? The most important thing is that we need to decide on the distributions. And then when we decide the distributions, that implies that we are deciding the dependency structures among these two variables. So let's think about it. So first thing we want to do is that we want to decide on the prior distribution over this z, that is the assignment random variable. And then what we're going to do is that we're going to say the log probability of z, so the assignment being k. So we're saying that, okay, the assignment to the kth cluster, what is the probability of that happening? Is the log of alpha k. So we're going to have large capital K many prior probabilities, right? And then in this case, what are the things that we know is that we are going to sum k goes from 1 to large K or d prime. So you can choose whatever you want, right? So we all know that these letters are there for our convenience, but there is the underlying truth that we are trying to access or refer to using these variables. So if we sum all these alpha values, they should sum to 1, and then they all have to be greater than equal to 0. Okay, so we have defined this prior distribution over this random variable z that reflects the assignment. So what it's saying is that without looking at the observation, what is our prior belief that the observation would belong to one of the kth clusters? So that's one, let's say, prior distribution. And then what we need is the likelihood or the generating distribution, as we learned about in the Bayesian machine learning. In Bayesian machine learning, what we had as a z was the theta or the weight variable, weight parameter, right? Weight matrix was a random variable there. And then we impose certain prior distribution on the random, that weight matrix. And then here, instead of the weight matrix, we're going to decide what the prior distribution is for this assignment variable z. And then in Bayesian machine learning, given the choice of the weight value that actually tells us about exactly which linear regression machine we are using, that machine in fact generated the output y given x. Now in this particular case of the k-means clustering or its generalization, we want to know, given the assignment, cluster assignment z, what is the chance that x, the observation, was generated? That is, we want to look at log p of x given z equals k. So if the assignment was set to be k, then what is the chance that we have created this observation x? And then we're going to, for now, simply say that it follows the Gaussian distribution with a mean that is dependent on the choice of the cluster k. And then we're going to simply say that our covariance matrix is going to be an identity. Identity covariance. Of course, there's absolutely no reason why we have to use the identity covariance. This could be full covariance, diagonal covariance, whatever you want. But for the convenience of the derivation today, we're going to stick to the identity covariance matrix. It also makes it easier for us to make the direct analogy or comparison against the original k-means clustering algorithms. And then this whole, let's say, procedure or this model can be graphically illustrated by having the random variable z. So we have a random variable z here. And then we have the random variable x. We have a random variable x. And then what we have is a directed edge going from z to x. And then what does this edge correspond to? This edge corresponds to the dependency structure that we have defined in this generating part. So we have the prior distribution over z. So we have z. And then given that z, we have a distribution over x that is conditioned on z. So we can succinctly describe the whole thing as this graph or the directed graph with the two nodes that corresponds to the assignment random variable and observation random variable with a single directed edge that goes from the assignment random variable down to our observation random variable. Okay, so once we do this, we can think about two different distributions here. One is a joint distribution. And then here, joint distribution refers to the joint between the observation and the assignment. So the log probability of x and z is going to be log probability of p of x given z plus log probability of p of z. Now, where does this equality comes from? This equality comes from the definition of the conditional probability that we have reviewed already in the one of the lab sessions earlier. And then furthermore, in this case, we can in fact compute the marginal distribution over x, so the observation very easily. And then that is going to be log p of x equals log of, we're going to sum over all the k clusters, right? And then when we sum them, we're going to look at the weighted sum of the normal probabilities or the probabilities assigned by the normal distribution across all those k clusters, mu k and 1. So again, this is the identity covariance. And then this alpha k is our prior belief. Prior belief that the observation belongs to the kth cluster without having seen the actual observation. So we have all these things here. And then what do we want to do? We know that what we want to do is to try to maximize these log marginal probabilities of the actual observations. Because we are working in the unsupervised learning domain, the data set we have consists of only the observations. There's no, let's say, labels here, right? So what we're given is a data set that consists of x1, x2, all the way to x capital N. So this is our data set. And then what we want to do is to maximize the sum 1 over n. Well, that's not really necessary. Let's try to remove the 1 over n factor because that's just a scalar multiplication, right? N goes from 1 to capital N log p of xn, and superscript. And what is it with respect to? We want to find mu 1 to mu k, and then alpha 1 to alpha k that maximizes this log probability. And of course, these log probabilities all depend on alpha k's as well as mu k's. So we can try to solve this problem directly. That's one way to do so. But it turned out that solving this problem directly requires a lot of, let's say, numerical issues. That is, we have to compute the log of the sum of all those, the normal, let's say, probabilities, and then we need to compute the gradient of that, and then we do the gradient descent gradient descent based optimization. It turned out that that's not necessarily the best thing we need to do. And then one of the reasons is that in this particular case of the generalization of the k-means, we could compute this marginal distribution exactly, assuming that this k, the number of clusters, is manageable. However, when we try to generalize it even further, it turned out that computing this marginal distribution or finding an analytical form of this marginal distribution is often impossible. So what we want is we want to come up with yet another way that allows us to apply the same algorithm to more general family of the probabilistic models. And that's where expectation maximization comes in. Maximization, okay. Or the EM algorithm comes in. So the goal is same. The goal is to maximize these log probabilities of all the observations after marginalizing out this hidden variable that is the assignment random variable. So the goal is exactly the same. However, we are not going to use the analytical form of this log marginal distribution. Instead, we're trying to use the joint distribution directly, because the joint distribution nicely factorizes into the log probability of the observation given the assignment and the log probability of the assignment itself. And then that is much easier to work with. But we'll see what it means. In order to understand the expectation maximization, we need to first introduce a so-called approximate posterior distribution, or some kind of distribution Q over the assignment vector or assignment random variable Z given X observation. And then this is going to be our categorical distribution. Why is it categorical? Because Z can take K many discrete items. And then what we want is that we want our Q to assign the probability to each and every K, the item out of K items. So then that naturally allows us to use a categorical distribution, although that's not the only way to go. And then what we're going to do is that we're going to say it's going to be beta 1x all the way to beta kx. So why do we have the dependency of x here? It's because this categorical distribution depends on x. So for every possible value x, we have a separate categorical distribution, and then that separate categorical distribution has its own parameters, that is beta 1x all the way to beta kx. So we're going to have as many betas as there are in the clusters, as well as there are observations x. And then given this categorical distribution, what we can do is we can try to consider looking at the KL divergence between the Q. So this, whatever the distribution that we decided to look into, Q of Z given X and the P of Z given X. If you remember from the Bayesian linear regression and the Bayesian machine learning earlier, this KL divergence or the Kullback-Leibler divergence is a very basic form of computing the difference between two different distributions. And then in particular, in this case, we're going to look at the KL divergence between this Q distribution that we have just introduced, and then the P of Z given X, that is the true posterior distribution. And you all remember what the posterior distribution is, right? Posterior distribution is trying to flip the arrows here. That is, we define our probabilistic graphical model or the probabilistic model, just like we did with the Bayesian linear regression, by defining a prior distribution over this unobserved assignment random variable Z, and then define the likelihood distribution of the observation given the assignment value. But then now the question is, given our observation, what should be the distribution over this assignment? And then in the Bayesian linear regression, it was given this data set, what should be the distribution over this Wayne matrix? And then here, what we have is that given this single observation, what should be the assignment distribution? And then that is the posterior distribution, and then that's written here. So what we want to know is that, okay, how much difference is there between this Q distribution and the true posterior distribution? And remember, true posterior distribution, we do not decide what that is. It's automatically decided based on our choice of the prior distribution and the likelihood distribution above. Like the distribution we made. And this KL divergence, let's write down his definition, is that it's an expectation over X, expectation over Z following the distribution Q, and then we look at the log ratio between the true posterior distribution and this Q distribution that we have just introduced. So let's say there is a question, what does the mu refers to in the maximization condition? Oh, so yes, so the mu, so we want to maximize this log probability of the observations with respect to mu and alpha. Where's the mu? Mu was the parameter for this likelihood distribution. That is, mu k refers to what is the mean of the Gaussian distribution that corresponds to the kth cluster. So let's continue. And then we can rewrite this as, we go for k, qz equals k given x, log p of z equals k given x, and then minus entropy of the qz given x. So this entropy tells us about how smooth the distribution is. So what is the maximally smooth distribution? In the case of the categorical distribution, if all these beta values are same, that is, all the beta values are going to be 1 over k, then they're summed to 1 nicely, and then they're maximally smooth. They are completely flat. Now, in that case, this entropy is going to be maximized. And what would be the case where this categorical distribution is minimally smooth? That is, one of these beta values take the value of 1, and then all the others are going to get 0. In that case, this entropy is going to be 0, that is minimal. But that's actually not that important in this case because it turned out that we're going to ignore this entropy eventually in our particular case. Now, continuing on from here, let's try to rewrite this k as q z equals k given x, and then log of the p of x and z equals k over p of x minus entropy q here. Oops, not k, but x. Now, how did we go from this, the posterior distribution, to this fractional, let's say, form? Is that again, we notice that this is nothing but the definition of the conditional distribution, right? So if you start from the joint probability of x and z, and if you divide it by the marginal probability of x, we end up with the probability of the z given x. So that's the posterior probability. So this looks kind of, let's say, weird thing to write down, but let's continue a bit further, then it's going to get much clearer. So what we end up with is that we're going to see that we have this is the first term we're going to get. This term comes from the denominator here. And then the next term is going to come from the numerator, the kind of, let's say, expected, right? P of x and z equals k. And then we have the usual entropy here. Okay, and then one thing you notice is that the log p of x does not depend on z. So log p of x does not depend on z. So what it means is that this term can come out of this summation. And then what do we know about this summation here? That is a sum of all the probabilities of the z under q, is that they have to sum to 1. That's what we know about the categorical distribution, or that's actually one of the fundamental properties of probabilities, right? What it means is that we can rewrite it as log p of x minus, and then now what is the second term? Second term is the expected log probability, expected log joint probability of x and z under this q distribution, right? Oops. qx and then log p of xc. And then now we have the entropy here, q z given x. So there's a question from Yukong. How do we get q in the first place? We didn't get any q. We just said that, okay, this q exists. So we want to have this q distribution for each and every observation. We haven't really got we haven't really got this from anywhere. So we just defined that, okay, there are these Q distributions, and that's about it. Okay, so far so good. So we have got log P of X, and then we have two terms that follow it. What it means is that, okay, we now know that the difference or the KL divergence going from the Q to P can be computed as the log P of X minus these two terms, or the sum of these two terms. And then here comes a really interesting thing. So this log P of X was what we wanted to maximize in the first place. And then one thing we need to notice is that this is greater than or equal to 0. Why is that? Because what we are computing here is identical or is equivalent to the KL divergence between Q and P. And then the divergence cannot be negative. So divergence has to be greater than or equal to 0. What it means is that this whole term on the right-hand side also has to be greater than or equal to 0. And then the weird thing is that here we can rewrite this as log P of X is greater than or equal to the expected joint log probability under Q plus the entropy of the Q distribution. And what it means is that this right-hand side is the lower bound to log P of X. And then this lower bound is tight. That is, this is going to be equality if this KL divergence is going to be 0. So what it means is that there are one thing we can do in order to make this lower bound that only depends on the joint probability and this Q distribution that we introduce without looking into the log probability, the actual marginal distribution. That is by making this Q distribution as similar as possible to the true posterior distribution. That is to minimize this KL divergence. And then our lower bound is going to be as close to as possible to the actual log marginal probability or the distribution. And now what it means is that if we have this lower bound, we can try to improve this lower bound instead of the actual log joint probability with respect to the actual joint probability. Now, this actually does remind you of something, right, that we learned earlier. What is that something? Is that we derive the log loss as well as the hinge loss from the point of view of looking at them as the upper bound to the 0-1 loss. So what we talked about earlier was that because minimizing the 0-1 loss directly is very, very difficult, what we want is to use the upper bound to the 0-1 loss, or a tight upper bound to 0-1 loss, such as log loss or the hinge loss, in order to minimize the 0-1 loss indirectly. Here, we have the same idea. In order to maximize this log P of X, there is a log marginal probability, which is often difficult to compute. What we want is that we want to maximize this lower bound. And then we want to maximize this lower bound with respect to both this Q distribution. And then when we try to maximize this lower bound with respect to the Q distribution, that's same as trying to minimize this KL divergence between this Q distribution and the true posterior distribution. That is, if we set the Q distribution to be identical to the posterior distribution, if we could, and in this particular case, we can do that, we'll see it soon, then we make this lower bound go up, thereby indirectly maximizing this log marginal probability. And then given this Q, we can now try to maximize this lower bound by changing this joint distribution as well. And then now this reminds us of the coordinate descent or the coordinate ascent procedure we talked about when we talked about the k-means clustering. That is, we want to maximize this lower bound by first maximizing this lower bound with respect to this Q distribution. And then this Q distribution can maximize the lower bound if we could set this Q distribution to be identical to this true posterior distribution. And then once we maximize the lower bound with respect to Q distribution. We're going to fix the Q distribution and trying to maximize the lower bound with respect to this joint distribution, which consists of the prior distribution and the likelihood distribution. It all kind of makes sense, right? Yes. And then we're going to look at each of the steps separately. And the first step that we're going to look at is maximize the lower bound with respect to Q. And then maximizing this lower bound with respect to Q turned out to be equivalent to set Q to be P of Z given X. Because this lower bound, maximizing this lower bound is equivalent to minimizing this KL divergence. And then if you could set Q to be exactly P here, then that's 0. That's the best way we can go. So what it means is that if we want to start from the joint probability, joint distribution, so that is log P of X given Z, and then we are going to rewrite it as the K, Z equals K. So we're going to go through all the clusters, K many clusters, and then see if this Z, the assignment, is K. That's the first term here, times the log of normal distributed probability of X given mu K and 1, that is the identity covariance, plus K. Now we look at the same thing, right? And then we look at the prior probability, that is a log of alpha K. So once we have this joint distribution, joint probability written, one thing we need to notice is that this true posterior distribution is also categorical. Why is it also categorical? Because there are K many different categories, and then we're going to compute the probabilities of all those K categories all independently, meaning that we are going to assign the probability to each category ourselves without considering all the others, as long as they sum to 1 and then they are non-negative. So what we need to do is we need to just move things around, and then what we notice is that the log PZ given X is going to be some constant, right? We are going to end up with some constant that is a normalizing constant, plus the log N X of mu Z, and then 1, that is the identity covariance, plus log alpha K, alpha not KZ, alpha Z. And then now these two terms here are going to be the numerators in the probability, and then this constant is going to be there to ensure that the probabilities are going to all sum to 1. What it means is that we are going to end up with the softmax formulation. That is, if we exponentiate these two terms, what we end up with is the alpha Z times the probability assigned to X given mu Z and identity covariance under the normal distribution. And then the denominator, the normalization constant that comes from this constant, right? This constant comes here. So let me just mark it here. Constant comes down here, should be the sum over all these values. Oops. It's going to be K, X, mu K, 1. And then this is going to be the normalization constant. So this is our categorical distribution we get. And then what we're going to say is that we're going to call this beta Kx. So what does it tell us? What it tells us is that the posterior probability of X belonging to one of the clusters is proportional to how likely this X is under the assumption given that X belongs to the Kth cluster or the Zth cluster. So what it means is that I have K many clusters, and then for each cluster, I have a Gaussian distribution defined in this input space, observation space. And then how it's defined is that each cluster tells us where the center of this Gaussian should be in this observation space. And then now given an observation, I want to know which cluster has likely generated this observation. And then how we are going to check is that for each and every cluster, we're going to test how likely this observation was under the likelihood distribution, that is normal distribution with the cluster specific center. And there's the beta z, that is the prior likelihood. Because even if the cluster was extremely likely to generate this observation, if the cluster's a priori chance of being selected is extremely low, then we don't really care about that, right? Because there was no chance to choose that cluster from the beginning. So this is the idea behind it. And then Jihoon, thanks for the comments. So this should be Z instead of K. So what it means is that if we are going to go through every single observation in our data set and then trying to figure out which cluster most likely generated this observation. And then we are not going to choose just one cluster, but we are going to compute that value for every possible cluster and then normalize them so that they sum to 1. And then that gives us this posterior distribution. Now let's just write it down a bit further. So we're going to write down P of log P of Z given X in a form that's going to be -1/2 X minus mu Z squared. So this one comes from the log of normal distribution given mu Z and 1 plus log alpha Z. So this is from the prior distribution plus some constant. And then often in the case of the K-means or any kind of clustering, we often don't have that much of the prior knowledge about which cluster is more likely, because if you remember, clusters do not have a given meaning to start with, right? So let's just assume that we don't care about this prior because alpha Z is going to be a constant. So then only thing that matters for this log posterior distribution is this L2's distance between the mu Z and our observation X. And if you think about it, this is exactly what we used in the K-means clustering. We computed the distance between the centroid of each cluster and the observation. So in one of the steps in K-means clustering, what we did was that given one observation, we computed the distance to all these cluster centroids. And then we said that, okay, this observation belongs to a cluster with the smallest distance between the corresponding centroid and the observation. And then here as well, we are computing the distance between this mu Z, which you could think of it as the centroid belonging to the Z cluster Z, and then the observation X. Only difference is that we are not going to choose a single cluster and then say that this observation belongs to that cluster, but rather we're going to try to softly assign the observation proportional to the distance or the inverse of the distance. So if there is a cluster whose centroid is really, really close to the observation, we are going to say this observation is highly likely to belong to this cluster, while with a cluster whose centroid is far and far away from this observation, we're going to say that is proportionally less likely to belong to that cluster. And then there is a question from Hao Yang, is that in this first step, are we assuming mu is known? Yes, we are assuming everything is fixed, including mu as well as alphas. Only thing that we are trying to compute is that the given mu's and alphas, what is the posterior distribution? That is the beta zx. And then this is just like in any kind of coordinate descent or the ascent procedure. And the one that we looked at the K-means, there, when we're trying to assign each observation to one of the K clusters, that is to infer the code vector to minimize the L2, the square Frobenius norm in the matrix factorization, we assume that the weight matrix was fixed. And here, that's exactly what we are doing. So now we know how to compute this beta value for every observation and the parameter. So, well, Jian, I think you are asking the exactly the question that I just answered. That is, we are going to do the coordinate descent. And in this first step, what we do is we are trying to estimate these Q distributions. And then there are as many Q distributions as there are observations, because this Q distribution depends on X. And then how do we maximize this lower bound with respect to Q is to simply set Q to be identical to the true posterior distribution. And then here we looked at how we can compute the true posterior distribution, which we're going to use as Q, that is the beta values. So, okay, so we now have obtained the Q distributions. And then given the Q distribution, we need to again maximize the lower bound with respect to, now what do we maximize it with respect to? Both alpha K, that is the prior probabilities of the observations, and then the mu K, that is the centroids of the clusters. So before we move on, let's answer one more question by Carol. How did we reduce the summation to L2 norm? Well, we don't have any summations here. So we don't have any summations. If you're asking about this denominator, there is a normalization constant, that's just a constant. The normalization constant does not depend on Z at all, right? So let's maximize the lower bound, but of course, we already forgot how the lower bound looks like, so I'm going to copy over this lower bound from down here. Let's see, copy, and then let's put it here, paste. Okay, so we have this lower bound here, and then we don't have to see what the lower bound is. And then the first thing we notice is that the alpha and mu K, so both alpha K and mu K only shows up in the first term. The second term is the entropy of the Q distribution. And then this entropy of Q distribution, of course, depends only on the Q distribution. And then the Q distribution was fully characterized by these beta values. And then it has nothing to do with alpha K's and mu K's that are used to define the prior and the likelihood distribution. Meaning that in this case, we don't care. We don't care. Now, then let's look at just this term. So we want to do it for alpha first. So we're going to write this J as a function of alpha. And then this J, the lower bound, I'm just going to use the lower bound here, is going to be sum over n. So here, the lower bound was defined for single observation. But what we want is that we want to maximize this lower bound with respect to the data set that we have, that consists of the n many observations. So that's why we want to look at sum over n, and then of course sum over k as well. And then here, because it's the expectation, for each k we have the beta kn, where the beta kn is essentially beta k xn, but for the simplicity, I'm going to remove the x there, times the log of the normal distribution, normal probability given to the nth observation, given mu k, and then the identity covariance plus log of alpha k, okay? And then, oops, I'm sorry, so I didn't need this one, okay? And then what I need is that this alpha values needs to sum to 1. That's really important, right? Because the alpha values define the probabilities of a categorical distribution, and they must sum to 1. And then in order to do that, what do we use? We use the Lagrangian multiplier. And then we learned about it in the, wait, hold on. Did we not learn about it? Okay, so have we learned about Lagrangian multiplier? If you have, please raise your hand. Use the yes or the raise hand button on the Zoom participant list. Looks like, okay. All right. Two of you actually, oh, okay. Bunch of you remember, so I'm going to just trust my gut feeling that I actually taught you what Lagrangian multiplier is, although I can't seem to remember where I taught you, but that's not important here. Okay. So then what we need is that we need to introduce the constraint that the sum of the alpha values is 1. And then how we impose that constraint is to use the Lagrangian multiplier. And to do so, I add the additional term in this lower bound term of the alpha, and then that is going to be lambda of k alpha k minus 1. In fact, it should be negative. So what we do is, first, we're going to compute the partial derivative of this j, that is a Lagrangian, let's say, formulation with respect to one of the alpha values. And then that's going to give you, so n goes all the way, so it's always a sum over n. And then what we have is here, only thing that matters is going to be this term, right? And then the first term, this term, does not really depend on the alpha k, so we can ignore it. And then what we end up with is beta kn over alpha k, because the derivative of the log of x is going to be 1 over x minus, what do we have here? We have the alpha k there as well, so we end up with the alpha. And then what we want is, we want to make it 0, that is to find the extremal point. And then this is going to give us lambda being sum over n alpha k over beta kn. Okay, so far so good. Well, actually, I'm sorry, that's precisely not what I wanted to do. In fact, that's precisely not what I wanted to do. What I want is that I want to find the extremal point with respect to alpha, because we computed the derivative with respect to alpha. So what it means is that the alpha k is going to be 1 over lambda, and then going from n, from 1 to large n, but I'm going to omit that, that's just taking too much space, then lambda kn. So we know that the solution is going to be in the form of the sum over n beta kn over lambda. Now we plug this alpha k back into this j in order to find this j Lagrangian multiplier, Lagrangian formation with respect to this lambda that is a Lagrangian actual multiplier, the coefficients. Then we go from n, 1 to large n, we go for k, 1 to large k, and then we have the beta kn. I'm not going to write down this first term here, because again, this first term does not depend on the alpha k. All I care about is where the alpha k shows up. And then what it means is that this is going to be the log of the 1 over lambda times the sum over the beta kn over k. And then what that gives me is that the log of sum over n beta kn minus the log of lambda, and then minus lambda, and then here I'm going to have the summation, but of course the lambda does not depend on k, so I can push lambda to the front, then sum over k, sum over n, beta kn, and minus 1. Okay, and interestingly, the first term here, this term does not depend on lambda at all, because the lambdas are going to cancel out, so we can in fact ignore this. We don't care about that. And then here in the first term as well, this term does not depend on lambda at all, so we can again ignore this. And what we are going to compute is trying to compute the gradient of or the derivative of j with respect to lambda. And then again, we still have the n, and then we're going to still have k in this case. Now lambda is there, so I'm going to put the minus sign in front, and I have the beta kn. And then what is the derivative of the log of x? That's going to be 1 over x, so it's going to be 1 over lambda here, so that I'm not making any weird mistake. Minus, here we still have, so what is the combination of this term and the minus 1? So minus lambda and minus 1, that's going to be just plus lambda, meaning that we're going to end up with 1 here. And then we want to find, again, another extremal point. So what we're trying to find with the Lagrangian method of Lagrangian multiplier is a saddle point, right? We want to maximize the objective function or the Lagrangian formation with respect to the variables that we want to estimate. And then we want to find among those extremal points, the point that's going to minimize this value with respect to this Lagrangian multiplier. So let's rewrite this. What it means is that the sum over n, sum over beta kn, lambda n is going to be 1. And then of course this lambda does not depend on either n nor k, so we can push this lambda to the other side. So n, k, kn is going to be lambda. And then what we notice is that this one is simply 1. Why is that? Because beta kn is the probability of the x or the nth observation belonging to kth cluster, and then it's a probability of the categorical distribution, and then we're summing all those probabilities over all those clusters. So it has to end up being 1. And then if we sum 1 n times, what happens? We end up with the n, meaning that the lambda is going to be large n, that is the size of the data set. And now we have this lambda equals n. What we want is we want to plug this lambda, that is n, back into this alpha k in order to get the actual value that's going to minimize this joint objective or the Lagrangian formula j. Let's put it back in. Then what we end up with is that the alpha k is going to be 1 over n, sum of the beta kn over n. Now let's think about what it actually computes. What it computes is that the first is going to compute all the probabilities are going to be all the probabilities that the observations belong to the kth cluster. Where's the k? Kth cluster is a kth cluster. So essentially, if you think about this beta in the extreme case where everything is going to be 0 except for one particular beta k given the nth observation, that's just like in k-means clustering. What this value is computing is the counting the number of observations that belong to the kth cluster. Oops. Number of observations, so that is the xn's that belong to the kth cluster. And then of course this belonging is solved. Belonging is solved. However, we can think of this as the number of observations. We are simply going to allow each observation or the fraction of each observation to belong to the kth cluster. And then we are dividing this number of observations with the number of all the observations. So this prior probability of the kth cluster is simply to look at how many of the data points that we have, and many data points we have, belong to this particular cluster. And then intuitively it makes sense, because if we didn't know anything about what each cluster means, all I can guess is that looking at the data set that I have collected, and then look at how many data points in that data set belong to that particular cluster, and then without looking at the new observation, I can simply guess a priori that that new observation that I could not see must belong to the kth cluster with the probability that is proportional to the number of training observations that belong to this cluster. So that's what we are doing. So there's a question from Hao Yang on, is strong duality guaranteed, or is it assumed in this problem? In this particular case, this duality actually exists. And then I haven't really shown it, but you can assume that that actually holds here in this case. This is in fact the same as coming from the k-means clustering, is that all these objective function that we have is convex with respect to the other. And then in this case, it's a convex problem, and having a Lagrangian multiplier that is a linear function is going to actually get us the exact, let's say, solution that satisfies the constraint that alpha k needs to sum to 1. However, that's a bit out of the scope of this course, but we're going to assume that that is possible. And then indeed, we have shown that we do get this solution for alpha case. Now, we found this alpha case, but alpha k was just one of them. What we need to find also is this mu k. And then this mu k only considers this first term. Now, we don't care about the prior, because the prior does not influence the likelihood distribution. So we're going to start from here, and then we're going to write down j mu as sum over n, and then sum over k. What we have is the beta kn, and then log n xn given mu k 1. And then this is it, because the prior term does not influence the actual choice of the likelihood. And also, importantly, there's no need for introducing any kind of Lagrangian multiplier in this case. Why is that? Because we do not have any assumption or the constraints on what this mu k could be. Of course, if you wanted, you could do that, right? And then you're going to end up with some kind of non-negative matrix factorization by imposing mu k to be positive, for instance. However, in this case, we're not going to assume any of that. And then now what can we do? We compute the partial derivative of this j with respect to one of mu's we have. Then, of course, summation over n survives, but we're going to choose only one of the terms from this summation over the clusters. What it means is that we get a beta kn, and then, wait, yes. We look at, let's move things around a bit. We're going to have the minus 1/2 coming out, and we have the xn minus mu k squared. And we want this to be 0 because we want to again find the extremum point. And then in this case, this is a complex problem. If we can solve it, the analytical solution we're going to get is going to be the exact solution to minimize this j of mu. And then in this case, oops, wait, no, I'm sorry. I am sorry. What I'm going to do is I'm going to call it just j of mu here. There was just another way to put it. And then if I write it as the partial derivative of j with respect to mu k, that's when I end up with n beta kn xn minus mu k. And then this is going to be plus. And then we want it to be 0. And then this one, if you rewrite things out, then mu k should be the n beta kn xn over sum of n beta kn. Now let's look at this formula a bit more closely. First thing we notice that we actually do see something similar to how we computed alpha k. What was alpha k? Alpha k was computed as the fraction. Well, alpha k was computed as the sum of all those beta k's across n many observations divided by the number of observations, or the total number of observations, that is n. And then there we said that the numerator was the number of observations that belong to the kth cluster. And then we allowed a fraction of observations. And then here, denominator of this mu k is exactly the numerator of this alpha k, meaning that we are going to look at all the observations that belong to this kth cluster. And then what we do is we are going to sum all those observations. So that's going to be our numerator. However, all those observations are going to be weighted by how much, by the fraction of this nth observation that belong to this kth cluster. Now, let's just imagine that this beta kn is the extreme and can take only 0 or 1. Then what it means is that the numerator is going to simply sum all the observations that belong to the kth cluster. And then the denominator is going to count how many such observations there are. And then that's simply taking the average of the observations that belong to this kth cluster. And that's precisely what we did 2 weeks ago in order to compute the centroids, or the weight matrix of the k-means cluster. This is just a generalized form of that, where we allow the fraction of each observation to belong to any one of the k clusters. So what it means is that we ended up building a k-means clustering, or the generalized k-means clustering, from the perspective of the probabilistic modeling, where we had the assignment, that is the code vector, as a random variable. And then instead of having a weight matrix, we had the Gaussian distributions, where the means of those Gaussian distributions corresponded to the centroids in the k-means clustering. And then by looking at this whole formula, we're going to go up. And then, okay, before we go on, we have these 2 stages. We have to alternate between them over and over until the whole thing converges. So we are going to maximize the lower bound by estimating q, fix the q. We maximize the lower bound by estimating alpha k and mu k, fix them. and then we're going to update the Q again to maximize the lower bound. We go back and forth, and then eventually it's going to converge to one of the solutions. And then now let's go up all the way to the original formula that we had. So what we had is that we had the random variable that tells us about the assignment, that was Z. And then this Z could take one of the K many values that had. And then we had the likelihood distribution that was just Gaussian, that is conditioned on the choice of the value of Z. And then in other words, for each K, for each value the random variable Z could take, we had one Gaussian distribution. And then that's how we ended up with the marginal distribution that was the weighted sum or the convex sum of the normal probabilities or the normal distributions, where the coefficients come from this prior distribution. And then this is why we call this whole model a mixture of Gaussians. Oops. So this is what we learned today that we have derived from the very first principle of the probabilistic model. So we started having this graphical model that models this k-means clustering by assuming how observation was generated. How was observation generated? We're going to sample the cluster according to this prior distribution, and then we look at the associated Gaussian distribution and then sample this Gaussian distribution. And then what we do is we wanted to see what is the best generating process given the data set consisting of n many data points. And then once we do that, we get the mixture of Gaussians. Now, why do we want with this mixture of Gaussians instead of the k-means clustering? There are many different reasons to use mixture of Gaussians instead of k-means clustering. And one of the reasons is that we can be much more flexible about this Gaussian distribution here. The Gaussian distribution here. Of course, for the simplicity of the derivation today, we assume that the covariance of each and every mixture component that is a Gaussian conditioned on the cluster assignment was identity, but it doesn't have to be identity. It can be full covariance matrix or diagonal covariance matrix, which is going to change. What is it going to change? Is that it's going to change how we compute these beta values, because how we computed the beta value was just looking at the L2 Euclidean distance. However, if this covariance of each mixture is not going to be an identity, this is not going to be just a Euclidean distance between the centroid and the observation, but it's going to be so-called Mahalanobis distance. That is, we're going to scale the different dimensions differently according to a covariance matrix, and then compute the L2 distance after this transformation. And then that is not easy to do with the k-means clustering, because finding out what is the right covariance structure is very different. However, in this framework of the mixture of Gaussian with the expectation maximization algorithm, we can simply compute or estimate the covariance matrices of all those Gaussians directly to maximize this lower bound we have. So that's one advantage. And then the second advantage is that we are not committing to assigning each observation to only one cluster. We are always leaving some chance that this observation may belong to other clusters, and then that turned out to be a very powerful signal that makes the optimization easier. And then this optimization does not get stuck at one of the bad local minimum more easily, unlike the k-means clustering, which almost inevitably will get stuck at a bad local minimum, and then you have to restart it over and over. But the third thing, the most important thing that I wanted to point out, or the third most important advantage of the mixture of Gaussian over the k-means clustering, is that the mixture of Gaussian allows us to compute the quality of the clustering. So, oops, I'm sorry, let's just. So mixture of Gaussian allows us to compute the quality of clustering. So how do we actually compute this quality? So the one nice thing about this mixture of Gaussian is that we now have a very nice formulation of the marginal distribution. So let's copy over this marginal distribution, copy, and then we come down here. And then what we see is that having this marginal distribution is great, not only because we can try to maximize this directly, however, because we can now compute the marginal probability of a held outset. And then this marginal probability turned out to be, in fact, very robust to the choice of our hyperparameters, where the hyperparameter choice includes whether we are going to use the identity covariance or not, but also the number of clusters. And then the held out set here is a validation set. So what that means is that once we estimate alphas and mu's, we can now compute the probabilities of the validation observations. And then the validation log marginal probability, so here, is going to tell us the quality of that, quality of the clustering. And then what we can do is we can now choose the K, the number of clusters, according to this validation log marginal probability. And that is the power of using mixture of Gaussian. And then that is the reason why mixture of Gaussian has been used quite a lot instead of the K-means clustering. Furthermore, of course, if you wanted to talk about even more advantages of the mixture of Gaussian, what we end up with is that we end up with the generalized form of mixture of Gaussian, that is the mixture of experts, where the expert could be anything, including Gaussian. So we could have the mixture of Bernoulli distributions if our observation is binary vectors instead of the real value vectors. If you know that our observations are non-negative real values, then we probably want to use exponential distribution or log normal distribution instead of the Gaussian distribution. And we end up with a mixture of exponential distributions, which in fact makes it very, very similar to the non-negative matrix factorization. And now, of course, we can go further and then try to generalize it so that it's not going to be simply a mixture, as in the random variable Z is going to be a categorical distribution, but Z could also be any kind of distribution we can imagine. And it can be a real valued vectors. And then we end up with a probabilistic principal complement analysis, which is a beautiful model, except that we don't really have time to go through that, unfortunately. And the interesting thing is that the probabilistic PCA was invented and proposed at NYU earlier. And then it's been used quite well. So that actually concludes what I have prepared for today. So in the lab session on Wednesday, you are going to see how mixture of Gaussian works and then how it compares to K-means clustering. Of course, comparing these two different algorithms is never trivial, but we're going to see what we get out of the mixture of Gaussian because we model each mixture of the cluster as having its own distribution. So that actually concludes it. Before we finish our lecture, let me just remind you once more about the announcement I made earlier today and also on Campus Wire. Final exam is going to be open book online exam conducted over Gradescope. I put the Gradescope link already in Campus Wire and also in the syllabus. Please do go there and then register and then wait for the follow-up announcement on when the online assignment is going to be available. You are going to be given 3 days to answer all the questions. And then it's open book, look up, Google the question, whatever you want, and then trying to answer it. The goal is for you to learn all those materials. However, please do try to answer all those questions on your own without talking with your your peers. And then the second thing is that the homework assignment policy has changed starting from the 3rd homework assignment. Even if you haven't submitted it, you're not going to fail the course. You're just going to get a low score for the particular homework assignment. However, we're going to curb the scores eventually at the very end, so you don't have to worry too much about it. And then you can always recover that by solving the problems in the final exam as well as you can. And if there's any more questions, I'm going to wrap it up and I'm going to upload the recording of this lecture as soon as it's available on Zoom Cloud Recording. All right, class dismissed. I'll see you all on Wednesday and next week.